Miss Scott with a video here on exceptions to Mendel's rules. Today we're looking at sex-linked traits. So let's start with, what is a sex-linked trait? It's a trait that's coded for by a gene that is found on the sex chromosomes. Now the sex chromosomes, if you're looking at them on a karyotype like we have here, are always shown as the very last pair. In females have two X chromosomes. They are the larger size chromosomes. And males have one X chromosome and one Y. So it's a clear difference if you're looking at a karyotype as to if you're looking at a male or female. This difference in chromosome structure will have an impact on how particular traits are inherited from one generation to the next. And being male or female will change your likelihood of inheriting certain sex-linked traits. I'll go ahead and preface by saying most of the sex-linked traits that we're going to look at are what are called X-linked, which means they're found on the X chromosome. There are such things as Y-linked traits, which, as you can guess by their name, are transmitted on the Y chromosome. And those particular traits are always passed from father to son. Father donates a Y chromosome to male offspring. But we're going to look at X-linked traits because everybody has an X chromosome, at least one. All right? We're looking at the alleles. Remember, an allele is a different version of a trait, and we use the allele letters in our punnett squares. We have X big H, which would be a dominant trait. Again, I'll preface by saying not only are we looking at X-linked traits, but we're going to be looking with examples like hemophilia and colorblindness, which are X-linked traits and are recessive. So if we're looking at an allele like this, where it's X big H, this is a chromosome that's carrying an allele that does not code for this particular disorder like hemophilia. This would be normal. X little h is a recessive allele, and that would, if you only had the recessive alleles like this, you would express the trait, in this case hemophilia or colorblindness. Now Y is an interesting chromosome. Remember, like we said earlier, the Y chromosome is shorter than the X chromosome, which means it doesn't have locations for all the alleles that are on the X. So the Y chromosome, we don't use these superscripts because it doesn't actually carry the copy of the allele that we're looking for. The allele we're looking for only resides on X chromosomes, which will make a difference. All right. Now let's take a look at the genotypes. Remember, the genotypes are the genetic makeup of an organism. I'm going to use hemophilia as my example, which is why I've chosen the letter H. Somebody who is X big H would be a female, two X's, homozygous dominant. And remember, hemophilia is a recessive trait, so being dominant or having a dominant allele would mean you don't have hemophilia, so she is not affected. You could also be, if you're a female, X big H, X little h would be female. She is heterozygous, and that has a special name with the X-linked trait. She is a carrier. And a carrier does not express the disorder, in this case hemophilia, but she can donate one of these recessive alleles to her offspring, but she would not express it herself. And then we have X little h, a female again, homozygous recessive. They would express that recessive trait, in this case hemophilia. This would be an affected individual. So there's three options for genotypes if you're a female with X-linked traits. With males, it's a tiny bit different. With males, remember males are XY. So X big HY, that would be male with a dominant allele. He would not be affected. This would be normal. Or X little HY, male, all recessive alleles, or only one recessive allele, and this individual would be affected. Note there's not a third option here because there's only one X. If you're a male, you either have the disorder because you have one dominant allele, or you express the disorder, you have it, because you have one recessive. You don't have the other allele, you don't have a second copy of the allele that can mask the recessive for you, which is why males tend to express those X-linked traits more than females. You tend to see hemophilia more in males and colorblindness in males as opposed to females. All right, so let's do a little bit of practice with a punnett square. These punnett squares always throw my students off, and there's really no need to because they're just like every other punnett square that you've ever done. You just got to set up the alleles slightly different. All right, so here's my example down here. I don't know if you can see that. We have a man who is colorblind marries a woman who is a carrier for colorblindness. All right. We want to know, there's a list of questions here. We want to know that if they have a son, what are the odds that he will be colorblind? If they have a daughter, what are the chances that she'll be colorblind or be a carrier? And could they have a child that doesn't have any trace of colorblind genes? So let's take a look, see? The first thing you need to do when you're building these punnett squares, you need to set up the sex chromosomes first. You need to establish that you have set up, your X's and Y's. So I'm going to put, there's mom, 2 X's, is a female, and here's dad, X, Y. That's the first thing. You have to have these sex chromosomes. That's going to tell you which offspring are male and which offspring are female. The second thing you need to do is add your little superscript alleles. And you're going to do this based on what you're told in the question. All right, we're told that dad, the man, is colorblind. All right? I'm going to use the letter B as my allele for blindness because capital C's and lowercase c's look a lot alike. So X big B, that would be normal vision. X little b, that would be colorblind. So dad is colorblind, which means he has the recessive allele on his X chromosome. And that's all I need to do. Remember, there's nothing on the Y chromosome. Nothing on this one because it's X-linked. Mom, we're told, is a woman who is a carrier for colorblindness. Remember, a carrier is heterozygous. So she has one normal allele and one recessive. And that's what you do to set it up. The third step we do is we're going to cross them just like every other punnett square that we've ever done. Again, it is, there's some formatting rules. You always, if you have X and Y, write the X chromosome first, and the dominant allele is written first, if one is present. So here we have X, big B, and X, little b, like we're playing Battleship, X, little b, X, little b, X, big B, Y, and then X, little b, Y. So now let's go back and answer our questions. We're asked, what is the probability that if this couple has a son, so we only want to look at male offspring here, that this son will be colorblind? So remember, sons are males, that would be XY, so I'm only looking at these two down here. Out of these two sons, this one will be colorblind, and this one will have normal vision. So 1 out of 2. There is a 50% chance that a son by these two people will be colorblind. If the couple has a daughter, there is a blank chance that she will be colorblind. So again, look at just the daughters, just the female offspring that have two X's. We have option 1, option 2. This offspring has both recessive alleles, so they'll show the recessive trait, which in this case is colorblindness. 1 out of 2. 50% chance that she'll be colorblind. The only other option out of the two is this one, which means there's a 50% chance that they will have a daughter, or 50% chance that any daughter they have will be a carrier. Could this couple have a child with no trace of colorblind genes? So we look at all of them overall, and we see that there is indeed a chance that they could have a child with no trace of colorblindness. That would be they only have dominant alleles, and that's this one right here. So this would be a son. So the answer to that is yes. Now look, if you have a male who expresses a recessive X-linked trait, all his daughters by default will have at least one of those, because daughters have inherited an X from mom and an X from dad. This is the only X that dad can donate, which is why all the daughters will always have some trace if the father is affected. If mom is affected, and we don't see it in this particular one, but let's just imagine for a moment that let's say this daughter goes on and gets married to somebody who is normal vision. Let's set that up real fast. If you have a female who is affected by a recessive trait, is there a chance that they'll have a child who does not have any trace of the gene? If your female is affected, all her children will have some trace of the gene, because that is the only type of X chromosome she can donate, and we all have at least one of those. Right? So if you have any questions, please leave them in the comments. The best way to master these kinds of punnett squares is to practice, practice, practice. So please feel free to go look up examples online and test yourself, and have a good day.